Okay, so here's something that is becoming really clear in the last few months. Harnesses are becoming more important than the model themselves. And turns out most of the harnesses that we use today, including the likes of Claude Code and Codex, were designed for the last generation of the models. Now, there is a new take on how to build a harness from a company called Prime Intellect. And their idea is to discard all the tools and scaffolding that traditional harnesses uses and replace everything with a simple IPython kernel. The results are incredible. They edged past the human expert score on ArcAGI 3. Now, there has been a lot of discussion around harnesses and this specific benchmark. So OpenAI recently showed that just by turning on two settings in their own harness, they tripled the score from about 13 to 38%. Claude Opus 5 currently leads the official leaderboard at 30. And this new harness takes the same Opus model and pushes it all the way to almost 95.5, just about the human expert baseline of 95.4. So in this video, we really want to deep dive into what exactly they are doing different. And then later on, I'll show you how to run this with DeepSeek 4 running entirely locally on DGX Spark. We also need to talk about this tendency of models and harnesses to cheat on benchmarks, and then its self-improvement loop made it even better at cheating. This is becoming a big problem in AI models and harnesses. So some context about Prime Intellect. It's a company really famous for RL. Now, for this specific harness, their idea is co-evolution of the model and the harness together, which I think is the right idea. So if you look at frontier models today, they are literally trained inside their harness. Cloud models around Claude Code, GPT models are trained inside Codex. So when a new generation of the model lands, the harness design actually lags behind. Now, Prime Agent is a bet on what harness should look like. Now the models are good at writing code. Now, this is essentially model agnostic. All the numbers that you're going to see comes from the models it has never seen, which means there is a lot of headroom still to get performance out of these models by carefully designing the harnesses. Okay, to understand what exactly is different about this, we need to think about how today's harnesses looks like. So they usually get a menu of tools for reading files, editing them, or running commands. Each one is described in JSON. So the model picks a tool and the harness basically runs it. And the results get passed into the conversation. And the same pattern repeats at every turn. So the context window of the model is going to grow as you're growing the conversation until it hits the context limits. And then the harness contracts the conversation, which basically means replacing your history with a summary. Now, summaries lose details. If the important thing was in the file that the agent read, let's say an hour ago, it is probably replaced by just a couple of lines. And we have all experienced this. You probably have seen your model starts forgetting earlier details. And this is one of the things they are trying to address in this new harness design. Now, Prime Agent premises that you don't need all of these tools. Their idea is that the model needs only one tool. In this case, it's a IPython kernel, which is basically a live Python session. Think about Jupyter notebooks. This is exactly the same engine behind it. Now, everything that happens is in Python. So if it needs to read a file, it is going to write Python. If it needs to run a shell command, again, it's going to be Python. Even if it needs to spawn a subagent, that is essentially going to be a Python function. So their idea is that rather than the model deciding to use one of the available tools, all it can do is simply write Python code and just execute that code. And the whole bet is that models are already great at writing codes. So this should be natural to the models. Also, the model only sees the final answer in the context. So it doesn't really see the code execution, but only the final answer. And that way, it's able to preserve the context window and keep it pristine. So you're basically replacing the arbitrary tool selection with a simple code writing task for the agent. Okay, so the Prime agent is built around this idea of RLM, or a recursive language model. So this comes from a recent paper, and actually the author of the paper is now part of the Prime Intellect team. So you could describe the idea in plain terms like this. A recursive language model is a model that can run code over its own context and call other models on pieces of it. Okay, so a simple analogy would be something like, for a normal LLM, it's reading an entire document at once, and then it has to keep that in its context window or metaphorical head. Then when it comes to RLM, it's basically flipping through pages as you need them. And then it uses subagents to essentially create summaries of long tasks and then just looking at the results. So this is essentially a division of labor. You can describe it in simple two moves. One is that context is going to be treated as a variable, and then subagents are parallel function calls. Okay, so let's first talk about how it deals with the context. So let's say you want to read a 500 kilobyte log file. Now, for a traditional harness, it's going to read the file and dump the whole thing into the context window. Let's say it's about 100,000 tokens. Now, in case of Prime Agent, the model writes something like this. So first, it's going to read the file in a Python variable, which is going to be in kernel's memory outside of the model context. And the model context is holding only that single line of code that it wrote. Now, when the model needs something, in their design, it looks at only 5,000 characters. So it's going to simply write a regular expression that is going to go over the error lines. And their whole idea is that the data is going to be on an auxiliary kernel that is sitting beside the model, and the model can just read things on demand. So in this case, the model doesn't really have to do compaction because all of the data is available to it on this auxiliary space. Now, they even snapshot the kernel to disk. So if a session gets killed, you actually still have that memory intact that you can read back, which is great. However, you also need to think about the size of the kernel. It's going to grow as the agent is taking more and more actions. And especially if you're going to persist it to disk, this is something that a separate process is running, and you need to account both for the memory and storage requirements. Now, for task delegation, it actually uses the concept of recursion from programming. And this is, I think, a very interesting piece. Right? So if you look at a traditional harness, if it triggers a helper, that will basically block the orchestrator. And the helper simply returns the results that gets passed on to the context of the orchestrator. Now, Prime Agent uses this idea of recursion. So for every subagent, it's basically calling itself. Essentially, you're pushing everything to a stack, and then when it returns, it will return back control to the parent. Now, the helper is full Prime Agent instance with its own context and its own kernel, and its answer comes back later as a message. Now, in terms of lineage, so agents can only talk to their parents, their siblings, and their children, which I think is kind of a limitation as well, because it really limits the inter-agent communication here. However, it also helps them stay sane at the same time. Okay, now let's talk about self-improvement, because I think this is the most interesting part. So the agent keeps a small version notebook about itself. This basically includes instructions on how to behave, memories about your project, skills, which are also saved as Python functions, and designs of subagents if there are any. Now, all of this gets injected into the system prompt. Whatever is in that notebook controls the behavior of your agent. Now, every 25 turns and so, a separate model pass reads over what just happened and makes the smallest edits that captures the lessons. So let's say if it failed the test twice, right, it's going to write that to memory. So essentially, you are giving the model or the agent a way to learn from its mistakes and experiences. Now, this is not weight changes, or you're not editing its own source code. the base prompt is immutable and every edit is version, which means that it can roll back. So essentially this is basically rewriting the instructions inside a contained environment. Now, I think this combination of working memory in the kernel plus the lessons accumulation actually contributed the most to the RKGI score. And we have seen similar pattern with OpenAI PT models as well, where they pushed it almost 3x compared to the base harness score. Okay, before we look at some of our own tests, I need to talk about some criticism of their approach as well. First, that 95.5% is self-reported. It's not the official ARC leaderboard score. And the Spectex point out that ARC is a few short benchmarks, so a harness that can save lessons between attempts might be getting more tries than the benchmark actually intends. This is the same criticism for the OpenAI results as well. Now, there's also a really interesting result from one of the maze benchmark where Codex or the same models explores 25 different rooms versus Prime Agent only 7, which means that managing context well is not exploring well. And this is, I think, going to be task dependent. Okay, now we need to talk about that cheating story that I mentioned in the beginning. So while playing Factorio, the agent discovered the game's admin console and started spawning resources directly, even though a prompt explicitly told it not to. Very interesting thing happened. So the refinement loop of the agent started saving better cheating skills rather than legitimate factory building skills. So the self-improvement machinery compounds whatever works, not what you actually meant. And this is the classic reward hacking that can happen in agents like these. Okay, so if you're still here, let me show you a demo on how exactly this looks like if you try to run it on your own hardware. Okay, so next I'm going to show you how to set this up on my local machine. So here's a link to the GitHub repo. We need to go to the installation instruction. Just copy this, run it in your terminal. I have already installed it, so I'm going to show you how to get started. Okay, so after installation, you need to use this command prime agent to start the agent. Now, the terminal user interface is going to look very similar to other coding agents that you have seen. When you start it for the first time, it's going to ask you for configuration. So you can actually use different models with this. So for example, if you see here, I have a DGX Spark cluster with 2 different DGX Sparks, thanks to the NVIDIA, running DeepSeek V4 Flash. That is my current model, the default model. I'll show you how to configure that in a minute. Also, you can go and you can provide your own API key or subscription if you want to use any model yourself. So for example, if I were to use Claude Code, I can just use my Claude subscription to sign in, or if you have one of these API keys from a provider, you can use that as well. Okay, so how exactly am I configuring DeepSeek cluster here? I can actually show you. So this is the configuration file where you want to define different models that you want to use. So right now in providers, I'm calling it Spark. This is the base URL. The model is running on the 2 DGX Sparks, and I am accessing it through the network. It's a OpenAI compatible completion point, and this is the model that I want to use. Now we can also look at the configurations in terms of settings. So I think it's settings.json, right? So this is going to set up the default model. Again, the model provider name is going to be Spark, and this is the exact model's string. Now I can use the model here inside the terminal user interface, or you can even use it in a headless fashion. Right now, I'm going to set the effort level to medium because I do want to use the reasoning capability. So for example, if I say something like hi, the first response takes some time, but you can see actually we are getting about 35 tokens per second, which is pretty good. And that's a single stream. For multi-stream, I have seen that can go up to almost 50 to 60 tokens per second. So for any agentic use case, this is going to be pretty good. Okay, so just to test the capability, I'm asking the agent to create an interactive Pokédex with 50 Pokemon, including animations and stats, right? And you can see that after that first prompt, the model is warmed up and it's pretty fast in response, which is pretty neat. This is a quasi-frontier model running completely locally in your own network, which is kind of incredible that you can use the second best open weight model that is out there today on 2 DGX Sparks. Okay, so something special that we discussed, every action that it takes is basically Python code that it writes in the Python kernel. So that was like one command. Here is, I think it needs to look at the context, basically use the list append command, right? So any actions that it's taking is essentially Python commands running inside that IPython kernel. Okay, so it actually completed the task, and right now it's using about 18,000 tokens in the context window. Actually, we can look at the context. So I think the total number of tokens that were generated are 94,000 tokens. Oh, that's probably what's actually left. Okay, so 18,000 input tokens, output tokens are around 8,000, 68,000 tokens cache read, and then the total comes out to be 94,000, right? So actually pretty impressive, and I'll show you. It's pretty great at preserving the context. So I ran an experiment on DGX Sparks on the same model with different harnesses, and this is one of the best harness out there on my internal benchmark. I'm hosting only the 128,000 token context, not the full 1 million, because I'm running quite a few things on the DGX Spark cluster. Here's the output, which is not bad at all. You can actually see that all of the Pokemons are animating pretty nice. You can click on them. It gives you further information about each one of them. Basically, all the functionalities are there. You can filter them out, right? So it does a pretty good job. Now, this is a relatively easier task, but still the harness is actually pretty decent. Okay, so let's have a quick look at this benchmark that I'm creating. Right now, it's a work in progress, but I'm seeing some really interesting trends here. Okay, so this contains 20 different questions from easy, medium, and hard, and everything is running the DeepSeek V4 Flash, and I'm comparing different harnesses. Now, there is going to be a more complex version of this coming out pretty soon, but from what I see right now is all of the harnesses are doing really well. Codex, OpenCode were lagging behind on a few tasks, and Pi also lags a little bit behind, but this is mostly noise, so I won't really pay too much attention to the success rate at this point. However, the main interesting things is the context, number of calls, number of tools that these different harnesses use. Okay, so I picked the ones that got 100% success rate, and you can see Prime Intellect or the Prime Agent harness uses substantially less tokens compared to something like Claude Code, because Claude Code tends to read each and every file. It's a very similar pattern with Kimi CLI as well. They don't take a lot of actions, but they take bigger actions. On the contrary, Prime Agent seems to be a lot more surgical, and since it's based on Pi, which in itself is a really good harness at preserving context, this actually does very similar things. So here's the token distribution for all of the harnesses. Pi uses the least amount of tokens. Claude Code is really token hungry, and that's why if you use the same model in either of these harnesses, you are going to probably get really similar results in terms of performance, but the bill is going to be very different. I'm going to share more on my blog post. By the way, I started writing technical blogs on my website. A link to it is going to be in the video description if you want to learn more. There's going to be a lot of content on harness design, agent design, context management, and I think you're going to like it. Both me and Claude are writing this. So if that something interests you, I'll put a link to it in the video description. Anyways, do let me know what are your thoughts, what is your favorite harness, and what are the different strengths and weaknesses that you notice. Anyways, I hope you found this video useful. Thanks for watching, and as always, see you in the next one.